All right, get a full screen. Not sure what to call this video. I don't know whether to call it Algebra 1 to Calc again, because that's what we're going to do. But we're really heavy on the Algebra 1 to get there. All right, so let's just have at it. Calculus is all about rates to amounts, and then amounts to rates. I'm going to be heavy on the rates side of things right now. Going to give you a very familiar function to work with, y equals x squared. And we're just going to do some Algebra 1 average rates of change. So from this function, which should have some coordinates that look very familiar, we are going to take values on the curve, and we're going to measure them each time to the coordinate 3, 9. We're going to do y2 minus y1 over x2 minus x1. Then we're going to look at some trends. Okay, Renee, the card is on the sideline today because room set up for testing. So let's start with the rate of change from the coordinate 864 to 39. And we do the change in y, 55, the change in x, and we see that it's an 11-to-1 rate of change. Now, it's very hard to show that because everything's going to look vertical here. So I'm not drawing to scale, but what I am suggesting from this coordinate to that coordinate, on average, is changing at 11-to-1. Now, there is a place here that if I zoom in, I'm also going 11-to-1. You kind of see it, right? But at other places, if I draw tangents, those tangents aren't 11-to-1. This one's less, that one's more, but this is the average rate of change from this coordinate to that coordinate. All right, so now we're going to do from 3, 9 to 7, 49. I got to remember to center this camera each time. And so this used to be 864. And now, oh, my average rate of change, 40 divided by 4, is 10-to-1. It was 11-to-1. I'm bringing this dot closer to 3 to 9. And now it's 10-to-1 from this coordinate to that coordinate, from this place to this place. And in math, we call that displacement. That's my corny joke. Sorry. All right. Continuing to bring x2 closer to x1, 36 minus 9 is 27 divided by 3. And the average rate of change now is not 11-to-1, not 10-to-1. It appears to be 9-to-1. Interesting. Little trend here. You want to guess what it's going to be? At 5? 25? 25 minus 9, y2 minus y1, x2 minus x1, 8-to-1. So we went from 11-to-1 to 10-to-1 to 9-to-1 to 8-to-1. I wonder what the next one's going to be. Let's find out. Oh, from 4. 16 minus, yes, 7-to-1. Well, it seems to me that we're headed towards, and this is the slope here, it almost looks like a tangent, right? But I'm bringing this closer and closer and closer. How about I bring it really close? Let's go over here. And if I get two places really close, which is still Algebra 1, I can find a place really close. I can subtract the y's, subtract the change in x, and I get a feeling for a comparison of the change of the outputs of the calculation divided by the change on the input side of things. I got a feeling we're going to get a 6-to-1 ratio of change at x equals 3. So let's look at a place close to 3. I don't know what you think is close to 3. I think 3.000001. It puts two coordinates very close, and I got a feeling I can see how the table values are changing by computing that. Don't need a calculator. 1, 2, 3, 4, 5, 6 decimal places. 1, 2, 3, 4, 5, 6 decimal places. We'll put it in a calculator. That's what you're going to get. 1, 2, 3, 4, 5, 6. That's what you're going to get. Now, what's the change? I think the change is 0.003456. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's the change in X, because the 3's are going to cancel. The change in Y, that's 10, 100,000, 10,000, 100,000. This is really a million times smaller than that digit place. I think we can ignore that and just do 0.00001, 2, 3, 4, 5, 6, 7. And I think, 6 to 1, which I'm hoping, if I said, what's the change at 3? We went from the change at 8, 11 to 1, was it? Trying to remember. Then I went to 10 to 1, right? So I think we found a way of figuring out how things are changing in an instant. Now, we're talking about squaring. Well, squaring has a picture associated with it. It's called a square. 3 times 3 is 9. And if I increase that, and I have to show you some increase, I mean, it's really just a little layer of area I'm putting in, right? That's 0.001, for instance. Then that's 3. This is 0.001, and then that's 3. Well, the new area is 0.003 and another 0.003, and that's 0.006, and I changed by 0.001. There's the 6 to 1. It's not quite as accurate as the other one, because the other one had more decimal places. I wonder what it would be if it was 2. Well, that would be 4. And that wouldn't be 3 anymore. That would be 2. Oh, that would be 4 now. So at 2, the rate of change of this quadratic, let's just put the quadratic there. The rate of change, we'll just say at 2, it's 4. At 3, it's 6. Any guesses what it might be at 4? Well, then that's a 4, and that's a 4, and that's a 4, and that's a 4, and that's a 4. Sure looks like at 4, I get 8 to 1. I wonder what it is at 5. Got a feeling it's 10 to 1. I got a feeling that no matter what X I put there, I think I'm just doubling it. Okay. So now I know that at 0, let's do this. No area, 2 times 0 is 0. 1, 2 times 1 is 2. So at 0, I have a flat rate of change. And then at 1, I'm going up at 2 to 1. And then at 2, I'm going up at 4 to 1. And at 3, I'm going up at 6 to 1. I'm starting to see how and why the quadratic in a continuous fashion looks like that. How about -1? We don't want to discriminate against negative numbers. -2, -2, -4. Oh, at -1, I'm coming down at 2 to 1, coming down at 4 to 1. All right. So there's the numerics that supports that. 1, 2 to 1, 2, 4 to 1, 3. Well, I was going to do this out, but I guess I kind of already did. All right, so how does that help us? Well, let's use capital Q, x squared, and let's call Q prime. Let's just make a symbol there and just read it as Q prime. And that's the way this function is changing. And we just figured out it's 2 times x. So what if I was at the location, let's say -1. I know the area squared is, let's move that over here a little more. If I square that, I get +1. Question is, at what rate am I changing there? Well, we just figured it out. Minus 2 to 1, doubling this x value. Well, I think that allows me to write the equation of the tangent line. I think negative 1, 1. Can see this. I think I write x plus 1 plus 1. And I think I have the slope. And so that tangent line tells me, let's say, an input, what the output is, and how the table is changing at that instant. Now, how can that help us? Well, it helps you to understand slope better. That's for sure. This conversation should. But 3x squared, I know x squared is changing by 2x. And if I triple that, I think I triple the rate. You were earning $10 an hour. I said, I'm going to double your wage. I think you got a real quick understanding of that multiplies into the rate. So what would this rate function be then? And how could it help us? Well, I think 2x times 3 is 6x. I think all I have to do is multiply that and drop it down 1. And I think a linear function, constant rate of change, and I don't think that number's changing. And if you see it change, constants don't change. If you see that number change in the next 10 seconds, please give me a call. So why is that helpful? Well, not proving why this is concave up yet, but we kind of know, from an intuitive standpoint, or whatever word I want to use, we know that that's what this general shape is. And what's the slope at the vertex? Well, if I zoom in, the more I zoom in, right, the more the curve disappears and the more it looks linear. And the slope of a flat line is 0. And this is what's telling me the slopes at any instant here. You tell me when that equals 0. I think when x is 2. Well, come up here now and do minus b over 2a. Because that's what we've been doing so far. Minus b, 12 divided by 2 times 3, 6. Oh my goodness, what a coincidence. It's also 2. What would the slope formula be for this calculation? I hope you say 4x plus 17. So that tells me slopes at any instant. Well, let's get an instant. Let's let x equal 0. Oh, I get 17. I wonder what the equation of the line tangent to this function is at 17. Well, 17 is certainly someplace going up. I think it's over here. Yeah, I think somewhere over there. I'm going to get a 0, 0, 3. And it appears like I'm going up at 17 to 1. Well, why don't we put that in slope-intercept form? Y equals mx plus b. The slope is 17, and the y-intercept was 3. Oh, what a coincidence. My, what a coincidence. Yeah, let's put some zeros in here. See if that's really true. Let's go back to Algebra 1. Let's see. Let's do x. Let's do 2x squared plus 17x plus 3. Let's throw a 0 in. I think that's what I get. I think I get 3. Let's throw 0.001 in. Well, if I square that and double it, I get 0.000002. If I multiply that by 17, I get 0.017, and I still have a 3. I don't see any change there. How would you describe that change? I would say negligible. It looks like this is changing at 0 by 0.017 divided by 0.0010. Oh, another coincidence, 17 to 1. All right, so let's have added over here. Let's see, I'm going to need another desk, or Rene. I can put Rene Descartes to the task by moving a desk. Bringing Rene over. Tell I have to plan this out. Let's put the cart right there. Cart right. Going back to Bonanza. All right. So let's do graphing, but using a little bit of Algebra 1 calculus. Can you tell me what the formula is for rate of change of that function? Maybe you can. 4x minus 5. Minus 20, excuse me. All right, what are we going to do graphing here? We're going to use minus b over 2a. That's 5. And what did we say happens at 5? Well, that's where we're going to be flat. We can find that by setting this to 0. Oh, what a coincidence. X equals 5. So I guess we're going to put 5 back in. We're going to put 5 back in. And if we do, we get minus 50 plus 17 plus 7. Same thing over here, minus 50 plus 7. And that's minus 43. So that would be the same. Now, how does this formula help us at the y-intercept? Well, we know that's the tangent. We know that's the tangent. So you're on the decreasing side, 0, 7's got to be over here. Now, what's the beauty of this? Well, if I wanted a tangent line at 6, well, I need to know the y value at 6. I can plug it in and find out. 36 times 2, 72, minus 120 plus 7. Didn't take long. 79 is 41 units, so I think it's negative 41. I think I made a mistake because I think I should be negative 39. So let's go find out. Because I know just squaring, I change by 2 units. But if I'm doubling that, I should change by 4. So let's plug 6 in again. 72 is right. Minus 120 plus 7. 72 plus 7 is 79. 79, that's 41. Oh, because I only changed by 1. Yeah, that's right. All right, should be negative. Thought I had a little different answer. Anyway, if I plug in 6 here, 4 times 6, 24, minus 20. Oh, okay, that makes sense. So 24 minus 20, there's the 4 to 1. Equation of that tangent line, 4x minus 6 minus 41. That's the equation of that tangent. It gives me information. So if I was saying that this is where grandma is on Route 91 at any moment of the day, and this is her velocity, then 6 hours from now, she's 41 miles south of the Vermont-Mass border, traveling at 4 miles an hour. Well, by God, that's why we study math. We got to go out there and help poor grandma. So if anybody ever asks you why you study math, talk about, in case you have to get out on Route 91 and help somebody. Yeah. And I think it's important you see that, because I don't think you're going to see the change in x. dx is what we use to signify changes in x that are really, really small, like 0.01. All right, and that's going to get me my change in y. Okay, so the change in y is coming from 2x's times dx. And in calculus, you're going to see that the change in y over the change in x is how we express y2 minus y1 over x2 minus x1 when we have a really small change in x. That means this is coming to the other side of the equation because it was multiplication. We have a formula. Now, what you're going to find is all the functions you're studying have formulas that tell you how things are changing in an instant. And they're not hard to learn. What's hard to learn is the conceptualization behind what we're talking about here. And I think it's important you start thinking about that now. And I've heard some very bright people who say, yeah, calculus gave them a hard time for months. Well, if all you're doing is do this, get that. If all I told you was, all right, let's just do a quadratic very quickly. I'm running out of ink. Let's do 5x squared minus 8x plus 11. Not a friendly quadratic. Minus b over 2a isn't friendly. But can you write the equation of the line tangent to this curve at x equals 3? All right, well, you need the formula for rate of change, which in this case is 10x minus 8. You plug in a 3, and I think we get out, what, 30 minus 8, 22. So I now know, I'm running out of room here, right? The slope is 22. That is 3. I only have to plug 3 in to find out my y value here, right? 45 minus 24 is 21 plus 11. 21 plus 11 is 32. All right. She's driving at 22 miles an hour. Better get out there again. Right, so this is where we're headed. And last thing I'll do is talk about the process that we actually did, since it is linked to something that we've been looking at. So let's look at the limit as x goes to 3. I went to 3 from 8 to 7 to 6, so on and so forth. I think I did that. And should have pointed this out a little earlier in the video, but running out of ink, I squared 8 and got 64. So in general, I was looking at the squared area, minus 9, over what? X minus 3. So when I put 8 in there, remember I did 8, we got an average rate of change of 64 minus 9, 55 divided by 5 was the first one we did, 11 minus 1. But these values, right, to 3, started at 8, went to 7, went to 6, went to 5, went to 4, went to 3.01, so on and so forth. I think that I'm changing my x's so that they're close to 3. That's 9, that's x squared. That's what I'm writing here. And Algebra 1 says you can reduce that fraction. Shouldn't be hard. X plus 3x minus 3. X minus 3's cancel. I plug 3 in. Looks like 6 to 1. Okay, so all the things you're studying now are going to support future efforts. And so I'm doing this to highlight that because I think you need to know where you're headed, what you're going to be studying. All right, and the calculus itself, lovely, lovely study, but only understood if you have a strong foundation. And I didn't talk about much other than Algebra 1 just then. It was all about y2 minus y1 over x2 minus x1 and plugging numbers back in. That's all it was. And I think if you see that now, it's going to help you in your future classes. So I'm doing it. And I want you to see it because I don't think you're going to see the geometric depictions enough. I don't think you're gonna, if you spend 2 or 3 days on this in a calc class and then move on, never see it again. I think you gotta see it often. All right, I'm rambling again. Have a good one.